At a basic level, a star is pretty simple. Gravity compresses the star as it tries to collapse, causing the inner core to overheat and condense. This triggers nuclear fusion, and the heat and pressure from it pushes back against gravity. When a star is in the main sequence state, the two forces balance each other out. But the details of how this works are extremely complex. Accurately modeling the interior of a star requires complex computer models, and even then it can be difficult to match a model to what we see on a star's surface. Now a new computer simulation is helping to change that. Although a star's internal pressure and gravitational weight are usually in balance, heat flow is not. All heat and energy produced in a stellar core must escape over time, and there are two general ways this can happen. The first is a radiative change. High-energy gamma rays scatter into nuclei in the core and gradually lose some energy as they migrate and escape to the surface. The interior of a star is so dense that it can take thousands of years. The second method is convective flow. Hot material near the center of a star tries to expand by pushing towards the surface. Meanwhile, cooler material near the surface condenses and sinks towards the core. Together, this creates a cyclical flow of material that transfers heat energy to the surface of the star. This convection agitates the interior of a star and is extremely difficult to model because of things like viscosity and turbulent eddies. Stars usually have a radiative zone and a convective zone. The position and size of these regions depend on the mass of a star. Small stars are almost entirely convective, while stars like the Sun have an inner radiating region and an outer convective region. For massive stars, this is reversed with an inner convective region and an outer radiative region. One of the things we know about convection is that it can cause the surface of a star to ripple, much like a boiling pot of water. This causes the overall brightness of a star to flicker slightly. In this new study, the team showed how convection zones in a star are linked to the way a star flickers. What they found was that the sound waves rippling through a star were affected by convective flows, which in turn changed the way a star flickered. This means, in principle, that we can study the interior of a star by observing the flicker of light, allowing astronomers to better understand the stars. Currently the vibrations are too small for current telescopes to observe, but we can study them with larger and more sensitive telescopes. We can already study the effects of sound waves on the Sun using what's known as helioseismology. In the coming decades, we should be able to do this with nearby stars. Scientists have computerized the sound of stars that seem to vibrate with the movement of gases on their surface. When you look at the sky at night, you may see stars that seem to blink or flicker rapidly. While this is mostly caused by the bending of light as it passes through our atmosphere, the main source can also be the star itself. Some of the pulsating stars in the sky can look like this because of the movement of gas on their surface. Scientists from Northwestern University, who studied these stars, gave us the opportunity to hear the sound of pulsating stars. Scientists simulated the energy between the core and outer surface of a giant star. He also mapped gas waves to predict how much a star should vibrate in the model created. The ripples obtained in the simulation were then processed called sonification, that is, they were converted into a sound. In the simulations, it was seen that as the size of the star increased, the sound became thicker and included more bass. With this difference, the stars even sang.